Okay. So, like I said, our goal today is to start related rates. I'll finish that tomorrow. Friday there will be a quiz on 3.4 and 3.5. Okay, so chain rule, general power rule, and implicit differentiation. And then we'll also start elasticity of demand on Friday, finish that on Monday. If everybody's looked at the schedule, I had an exam scheduled for next Tuesday, but I took an extra day to go over the first exam. So the exam's going to be next Wednesday, okay, so a week from today. I'm also I've been posting all those suggested textbook exercises, but I think what I'll do this time is when I post the review, I'm going to try and kind of maybe just make it like 10, 15 problems instead of like the 30 that I suggested last time. So hopefully that makes it less overwhelming. If you need more problems, there's more problems there. So I'll try and focus the review a little bit more this time. I'll also, instead of in class telling you what you need to know, I will this time at least print out a big review sheet with all the topics, what you should be able to do. So hopefully that'll kind of help organize your studying for the test a little bit better. Okay, so let's just do 3.5, a little more implicit differentiation. And then, like I said, hopefully I can maybe write the notation just a little bit different, because I think the hard part is understanding the idea. Once you get the idea, it technically, I don't think, is any harder than any of the derivatives we've already done. It's just getting comfortable with the idea. So what I'm going to do is I'm going to say, let's find y prime if we have an equation. I'll do something like 2x plus y squared plus 4xy equals 2. Okay. Now, again, it looks pretty complicated. What do we really need to do here? So to help you out, if I'm finding y prime, we're treating y as a function of x. So we're saying, let's just pretend y is the dependent variable and x is the independent variable. i.e., let's actually just write this. Let's write y equals y of x. That way you'll see the function notation. It might help you when you find the derivatives. So I'm going to rewrite the equation now. This is 2x plus y of x squared plus 4x y of x equals 2. Now you actually see y as a function. Okay. So everybody okay with what I did there? Instead of just leaving it as y and doing this, I'm actually going to rewrite y so it looks like a function. Okay, so that way you might it might be a little bit better. Now, what I'll do is I'll write this down for everybody. So now that we've rewritten y as y of x, all you're doing now is if you're taking derivatives of powers of y, it's really just the general power rule. You do n, the n comes out front, the inside stays the same, and you multiply by the derivative of the inside function y prime of x. Okay. So hopefully, I'm hoping that reintroducing this notation will make you see how to take derivatives a little bit better. So is everybody okay with what I did there? All I did was took the implicit equation, okay, and since I'm trying to find y prime, y is the dependent variable, x is the independent variable. So does everybody know what I mean when we say a dependent variable? It depends on the other variable. So instead of just writing y, let's make it look like y depends on x. Okay, so we're just writing y as a function of x. Okay. So like maybe you want to, y of x, you could think of it as being like 2x plus 4 or something. Unfortunately, though, we have to leave it as y of x. Okay, so first thing I'm going to do is there's a radical, right? And whenever we see radicals and we need to take derivatives, we always rewrite with?
Fractional exponent.
Yeah, we use the fractional exponent form. I think that's what you were saying, right, Sergey? You were about to say fractions. So the square root of that first term gets rewritten as to the 1/2 power. And like I said, rather than just leaving it as y, we've replaced y with y of x, so now it looks like a function. Okay. And then, what was the idea? To take a derivative implicitly, you take a derivative with respect to the independent variable. So if we're finding y prime and y is the dependent variable, that means we take a derivative with respect to x. Okay, so I'm going to do this. You don't have to write this in. You could just start taking derivatives if you want. So you take the derivative with respect to x, the independent variable on both sides. And I made this a little bit messy, but I think I could have made it worse. But. Okay. So now, first thing I'm going to take a derivative of is this 2x plus y of x squared to the 1/2. You're going to have to use this general power rule twice. You'll have to use it once on the outside, and then when you're taking the derivative of the inside, I'll have to do it again for the y of x squared. Okay, so now, let's just worry about this term first. In fact, let me underline it just so we know what we're working with. We're just taking the derivative of this for starters. Okay, so the general power rule says the 1/2 comes out front. And then what happens to the inside? It stays the same or nothing. So it's still 2x plus y of x squared. And then we raise it to the next lowest power. We subtract 1 from 1/2 and get minus 1/2. And then you always have to make sure you multiply by the derivative of the inside part. Now there's two terms. Probably going to run out of room, but I can use this side. Okay, so there's two terms on the inside. The derivative of 2x, so it's going to be 2 because we're taking, right, x is the independent variable. It's not a function, it's just a variable. Plus, and then now the y of x squared, which is really the y squared. Now you actually see the function notation on the inside. So you're just using, again, the general power rule. So the 2 comes out front. What happens to the inside part? Stays the same. What do you do to the old power? Subtract 1 first, so that's a first power. And then Reese, you were saying you also have to take the derivative of the inside. The derivative of y of x is y prime of x. So if you need to introduce function notation so you understand that really the dependent variable to a power, you're just using the general power rule on it. Right? So if it was just y squared, it would have just became 2y times y prime. But we'll stick with the function notation for now, and then I'll substitute back later. Okay? So that's just this first term. Now I want to take the derivative of this part. Okay, now what do you see here? What derivative rule would I want to use this time? Chain. So we don't need a chain rule because there's no compositions. Yeah, so what's the other term for multiplying? A product. There we go. So that's what so really, there's a product going on here. 4x is the first function, y of x is the second function. So now what I'm going to have is a plus. Okay, and then, let's see. It's going to be first function times the derivative of the second. Now the derivative of a function y of x is y prime. Okay. And then it's plus the second function, y of x, times the derivative of the first, and the derivative of 4x is 4. Okay, and that takes care. This was the derivative of the red part, and this was the derivative of the blue part using the product rule. And then the derivative of the 2 on the right would just give us a 0. I kind of picked one messy on purpose. I think if the algebra, if it was simple and it was a simple expression, I don't think solving for y prime would be that difficult. Okay, so I chose one a little bit more difficult on purpose so we can get practice on the algebra. Okay. Does that kind of help see it a little bit better instead of just writing y, if we write y of x instead? Is that maybe a little helpful?
Is that as simplified as you'll want it on the test?
No, because the original question said find y prime. So now we have to go through all the algebra to solve for y prime. But it's just like solving for any other variable, right? You multiply everything out. You want terms with y prime on one side, all the other stuff goes to the other. Okay, so at this point it is the same algebra we've always done. Okay. But we're going to go through it together. Okay. And I know it's going to look really messy, but it's just the way it is. So first of all, what I'm going to do is, in these parentheses, I have 2 terms, 2 and then 2y of x, y prime of x. Okay. And actually, I think what I'm going to do is I'm going to go back to y's, because it's a pain to write the y of x's all the time. So I can rewrite this now. Remember, if y equals y of x, that's the same as saying y prime is y prime of x. Okay, so now it's going to become 1/2 2x plus y squared to the minus 1/2. And then it's 2 plus 2y y prime, because the y of x becomes y and y prime of x is just y prime. And then I have plus 4x y prime plus 4y equals 0. So all the y prime of x's I just rewrote as y primes, and all the y of x's are just back in terms of y. Okay. And then let's see, I have to distribute this term to the 2 and then distribute this term to the 2y y prime. Okay. So 2 times this, the 2 and the 1/2 just become 1. So you get 2x plus y squared to the minus 1/2. That's for this distribution. And then I'll distribute to the second term. That's just going to be plus y prime 2x plus y squared to the minus 1/2. And by the way, on the test, I would never give you one this messy. Okay. But any chance we have to practice algebra is going to be good for us, whether we like it or not. And then I have the plus 4xy prime plus 4y equals 0. So which terms have y prime in them? Well, this term has a y prime and this term has a y prime.
Can you go back to that distribution?
Yep. Sure. Yep. Let me pause for a second.
I would take the 1/2 from the front.
So if I took this expression, 1/2 2x plus y squared to the minus 1/2, if I multiply that by 2, the 2 and the 1/2 just become positive 1. So I just get this. Well, folks, what's 2 times 1/2? And then what's left over? This. Okay. If I need to rewrite this for you,
Okay, right.
okay, all I'm really doing is something like 1/2 z times 2, where this is z. 1/2 z times 2 is z. Okay, where I'm treating this as my z. Okay. And then when I do this whole expression times the 2y y prime, the 2 and the 1/2 become 1, and I'm just left with y times y prime times this expression. You see it now?
Yep.
Okay.
Yeah. Thank you.
There's a lot of stuff all over the place, so. Okay. So any other questions? I don't want to go too fast. Okay. And then now what you're going to do, if you're trying to solve for a variable, you use that same rule that you might have learned back in an algebra class, is you want to keep terms with that variable on one side. The terms that don't have y prime, we're going to move to the other side. And I'm also going to factor. Y prime can be factored out of these two terms. So I'll get y prime times y2x plus y squared to the minus 1/2. If I factor y prime out of this term. And then it's plus 4x, because I also factored y prime out of this. Okay. And then I'm going to subtract this term and this term to the other side. So you get a minus 4y and a minus 2x plus y squared to the minus 1/2. So I did two steps. The terms without y prime, subtract to the right. The two terms that contained a y prime, I factored it out to the front. And now there's only one more step. I just have to divide both sides by that expression and we're done. So y prime and I'm not going to simplify this any further. I don't really see the point in doing it. But there's your y prime. So, yeah, a little bit messy. Algebra's a little bit messy. But I thought by doing a messy one that might help you with some of the harder ones on the homework. Does anyone want to maybe just do one more that's not so crazy? Just to kind of get this down one more time? Okay.
So,
yeah, what's up, Ollie?
Since that's to the negative 1/2, can it go down in the
It could if this was a multiplication right here, but since it's subtraction, the only thing you could do is maybe this could be rewritten as 1 over. This could also be rewritten as y divided by this. And then you'd have to multiply top and bottom to clear fractions. But so yeah, you could simplify it, but I'm not going to just go through it here. Yeah. As written, you could plug it into the calculator. So simplifying this stuff isn't as important as when you take a derivative of an explicitly defined function. The simplifying there is much more important than trying to mess with simplifying the expression for y prime here.
Okay.
Okay. It's not as important here as it is in the explicit cases. Okay. So let's do one more before I jump into the next. I'll try and make it not as bad this time. So let's say find y prime if you have xy squared plus e to the y equals x cubed. That doesn't look as bad, does it? There's no square roots in there. Now, I'm going to do this one more time. You don't have to do this on the test. Okay? You're treating y as the dependent variable, so it's a function of x. But maybe for practice, what we'll do, just so we can see y as a function of x, we'll replace y with y of x. Because then we can actually see it as a function. Yeah?
You said earlier that we could choose which one we wanted to make it dependent.
No. Once you're told find y prime,
okay.
That's telling you y is the dependent variable and x is the independent variable. Okay. And just so you know, another notation, sometimes you'll see them ask for, you'll see them say find dy dx. That's the same thing for y prime. This notation tells you what's on top. That's basically the change in the dependent variable over the change in the independent variable. Okay. Next section, we're going to use that dy dx notation because all variables are going to be dependent variables. The independent variable won't even be visible in the equations, which makes it kind of tricky as well. But okay, but it's the same idea here. So I'm going to do this one more time. In the next section, you probably won't see me do this as much. So I'm going to rewrite the equation now. You can replace all y's with y of x's. And now that I have an e to the y of x, let me remind everybody about the general derivative rule of e to a function. Anybody remember what it is?
the function comes down
So-
and multiplies with the original.
Okay, so Ollie said take the original and then multiply by the derivative of the
Yeah,
exponent.
that's
Yep,
fine.
comes down out front. Yeah, no, you're exactly correct. Okay. All right. So what about this first term? Let's do this first. I'm not going to write the d over dx on both sides either anymore. I'm just going to take the derivative of every term with respect to x. So ultimately what I see here, x is a function and y of x squared is a function. So again, we have a product. So we have to use the product rule. And how does it work again? You take the
First function times
So you take the
derivative
first function times the derivative of
of the second.
the second. So now this is a function to a power. We're just using the general power rule. So the 2 comes out front. The inside function y of x stays the same. In fact, I don't even need parentheses, do I? Since anything to the first power is itself. So the power comes out front. The inside stays the same, and then you have to multiply by the derivative of the inside, which would be y prime of x. If it was just y squared, you would write 2y y prime. Okay. And is that the whole derivative yet? That was just first times derivative of the second. Now it's plus the second function, y of x squared, times the derivative of x, which is 1. Plus, now the e, I just wrote this on the side, but e to a function, the derivative is the same thing, times the derivative of the exponent. And then what's the derivative of the x cubed on the right?
3x squared.
Yeah, x is the independent variable, so we just take the derivative like before, you get 3x squared. Okay. And again, I don't like the y of x's in there because I'm a math person, I'm lazy, and I hate carrying notation with me. So at this point, I would just translate back to y's. So you could write this as 2xy y prime. So I have 2 times x times y prime. Plus, y of x squared is really the same as y squared. Plus, this is just e to the y times y prime. Or if you like, you can write it this way, y prime e to the y. And that equals 3x squared. Okay. So let me pause for a minute. Let me let people get caught up and kind of digest that for a moment.
Reduced it one. That's y prime.
Oh, times right there.
Is there anybody that would want me to maybe come in this weekend? Like on Saturday or something? I can if there's anybody that requests it. Okay. You have until Friday to let me know. So if I don't hear anything by Friday, I'm just going to go fishing or something like that on Saturday. Okay. Or maybe just play some golf. That's about all I do. Watch movies, read books, play golf, go fishing, go camping. Okay. So now, if you're with me up to this point, ultimately we're trying to find y prime. Okay. So now what I need to do is just get terms with y prime on one side and move all the other stuff to the other side. So I think what I can do, and I'm going to skip some steps. This term and this term carry a y prime. I can factor it out. So you'd have y prime, you're left with 2xy, and then the other term had an e to the y. And then isn't there only one term to move to the right? We just have to subtract the y squared. So the right-hand side would just be 3x squared minus y squared. And then we just have to divide by the 2xy plus e to the y. Those will cancel. Y prime is 3x squared minus y squared over 2xy plus e to the y. You know it's cool. One of the points of doing this, you could go like plug this into Desmos. It's going to give you some crazy looking curve. Right? At any point on the curve with coordinates x, y, I could just plug them into this formula now, and that'll give me the slope of the tangent line to the curve. Okay, so that's the idea of what this is for. It's particularly useful in like physics when you have like motion of a particle, right? And the motion of that particle is represented by some curve like this. Maybe you want to find some rates of change in one direction or the other. Like what's your speed in the x direction, or what's your speed in the y direction? Something like that. And then, you know, the business and economics examples that are in this section, they're kind of contrived a little bit. But I think the whole point of this section is really just so we understand what related rates are. Okay. So keep this idea of implicit differentiation in your mind. We're going to start this today, finish it tomorrow.
Thank you.
Do you have any time for any homework questions?
Yeah, I can have one. Do you want to say?
I was wondering if you could go over 54 on the written.
54 on the written?
Yeah.
Is it just a function and a derivative, or?
Yeah, I can't remember exactly. I feel like it wanted something else, but I know you had to find the derivative.
Okay. Yeah, do you kind of have the question in front of you?
Yeah.
So number, you said 54,
Yeah.
and this is in 3.4?
3.5.
No, 3.5. Oh, okay. So x, hold on, that's the cube root of,
1500 minus p to the third.
so it's the cube root of 1500 minus p cubed?
Mm-hmm.
Okay, so this problem is just saying that demand x and the price p are related by the above. I'll just write equation above. Okay, so this is just the price-demand relationship. Okay. We would say x units are demanded at a price of p dollars. And does it say find p prime?
I know it wants the derivative. I can't remember what else it wanted. I don't have my computer with me.
Let me see if I can get it pulled up real quick. I guess maybe that's good that I did the radical implicit differentiation problem at the beginning. This will be somewhat similar. So my guess is that you're finding p prime, because if you were just finding the rate of change of demand with respect to price, you would just take the derivative of this like before. So my guess is they're saying find the rate of change of price, p, with respect to demand. Otherwise, this wouldn't be an implicit differentiation question. It would just be an explicit derivative from before. So that's my guess. My math lab is being really stupid right now. It has been all day. I don't know why I haven't been able to get on. Okay, so hopefully I can do this in about 5 minutes, because I want at least 15 minutes for the related rate stuff. Okay. So first of all, it says find the rate of change of price with respect to demand x, or the number of units demanded. That means you're finding p prime and you're treating x as the independent variable. So again, right, the rate of change of price with respect to demand x, this is basically just saying find dp over dx, which is the same as p prime. Now, I could replace p with p of x like I did before. I'm going to try and do one without switching the notation. Okay. So right, when we see p, we're really thinking p of x. It's a function of x. Okay. So if I want to take the derivative with respect to x on both sides, so take derivative of both sides with respect to demand x. So first of all, if I'm taking the derivative with respect to x, the derivative of the left-hand side is just 1. And let me rewrite the right-hand side because, like I said, radicals are almost useless. So that's the same as 1500 minus p cubed to the 1/3 power. So the derivative of the left is 1. And then what about on the right-hand side? So this is actually kind of similar to the one I did at the beginning of class. Okay, so we start by pulling out the 1/3. The inside stays the same. And then you reduce the power, you subtract 1. That'll give you a minus 2/3. Okay, and then I also need to now multiply by the derivative of the inside. Remember, p is p of x. So we're again essentially just using this derivative rule where p is replaced with p of x. So anybody have an idea? The derivative of the 1500 is 0. What's the derivative of the minus p cubed going to be?
Negative 3p squared p.
Yep. Right, it's really negative 3p of x squared times p prime of x. But that should ultimately be your goal. To help you see it being a function first, kind of do what I did in those first two. But once you get the hang of it, it's not really worth your time to replace p with p of x. You got to be seeing that in your head though. Okay. So once I know p is the dependent variable, I don't see a p, I see a p of x in my head. That's just because I've done it so many times. And then now you just need to solve for p prime. You can multiply both sides by 3 for starters. So you get 3 equals, actually, I don't have to do that. I've already got a negative 3 right here. So the 1/3 times negative 3 would just be negative 1. So let's do this. Let me just simplify this. This is minus 1500 minus p cubed to the negative 2/3 times p squared times p prime. So I just multiplied the 1/3 and the negative 3. And then now to solve for p prime, I just need to divide by this other stuff. I'll divide by this. P prime is going to be 1 over negative 1500 minus p cubed to the minus 2/3 times p squared. And this time I will simplify it, since it's easy to. Now since this is multiplication, remember in that first example you wondered about getting rid of the negative exponent? I can bring the negative up top. And then upstairs we can write to the positive 2/3, and then we still have that p squared in the denominator. And that would be p prime. And then we could find the rate of change of price with respect to demand x at any given price. Right? So if the price was $4 and I wanted the rate of change of price, I would just plug it in for p on the right. Okay.
So back when you distributed the 1/3 through, could you have taken just the 1/3 into that 3p p prime, and then?
Oh yeah, I guess I could have multiplied 1/3 by this and got minus p squared p prime.
And then move if you rewrote the 1500 minus p cubed,
The negative 2.
so if you go like 1 over that, and then multiply the other side?
Yeah, that's another way to do it too.
Okay. I think that's what I don't know. I think I got the same answer.
Yeah, I could have rewritten this as minus p squared p prime divided by this to the positive 2/3 and then mess with the algebra another way.
Okay.
So just so you know, when I do things algebraically, it's not the only way it can be done. This is what I see first. Question?
I sort of understand how you're getting rid of the 1/3, but why didn't you have to multiply to the 1500 instead of why did you get to choose?
Okay.
Yeah.
So if I do 2 times 4 times 5, why don't I multiply 2 by 4 and 5?
Oh, okay.
Right? I choose, I either multiply 2 by 4 first or by 5 first.
Okay.
It's the same idea, right? 1/3's a number, that's a number, that's a number, that's a number, that's a number. So I don't multiply 1/3 by more than one thing. I choose one thing to multiply it by, And the most convenient thing to multiply by 1/3 is the -3 over here.
Oh, that makes a lot more
Yeah, you see what I'm saying? Like, again, if you're doing any product, if I take a specific example, I don't multiply 2 by the other factors 4 and 5. I pick one of these to multiply 2 by first and then multiply by the result by the other. Okay, so it's the same idea, it's just you have variables. It's a good question though. Okay, other questions? Okay, I want to make sure I get a start on this. At least get through the first example so we can finish the other two tomorrow. Okay. Now, when you read the book, again, since the book isn't just a business calc book, it's a calculus for business, economics, life science, social science, natural science, yada, yada, yada. Some of the examples, the first few, are going to be about motion, or like, triangles where the sides are increasing in length or something like that. So if you look at the definition that I have here, number 1, it says sketch a figure if helpful. Well, for profit, revenue, cost, there's not really a geometric picture you can draw. So for us, most of the time, there is no step 1. There is no figure that you're going to sketch. Now, my note at the top, here's the point. In a related rates problem, you're given an expression involving certain quantities, or those quantities are represented by variables. Now, instead of one of them being the dependent variable and the other being the independent, this time we're going to treat all the variables implicitly as functions of time. Okay? And you'll see what I mean here in a second. And then we take the derivative with respect to t. And this is kind of weird because there are no t's in the formula. But don't we all know that profit, revenue, and cost, they depend on the number of units produced? But don't they also depend on time? Right? Like if a month passes, your cost is going to change. Right? Your profit and revenue and cost don't just depend on the number of units produced. Right? In reality, profit, revenue, and cost also depend on how much time has elapsed. So you don't see a t anywhere, okay, but there's really an invisible t floating around in the air. Right? Time is really influencing these things as well. Okay, it's just that up until now, all our profit, revenue, and cost functions were functions of the independent variables, x, the number of units produced. Now we're going to do a basic example, and then examples 2 and 3 will actually do the business and economics application. Okay, so related rates. So now, what I have here in this first problem is I have a relationship between x and y. So x squared plus 3xy equals 4. Okay. So not only is there a relationship between x and y are also varying with time. Okay. So that's this first part. It assumes there's a third variable. You're going to assume x is a function of time t. And again, you're also assuming that y is changing with respect to time t. Okay. Now, if you go back to this box, this definition box, number 1, sketch a figure if helpful. Again, for business and economics, there's really no geometry involved, so there's not really a picture you can draw. Express all given rates step 2, identify all relevant variables. For us, the variables that are relevant are x and y in this expression. Okay. And then including those whose rates are given and whose rates you're going to be finding. So these problems are always the same. You're given some expression relating variables. Then you're going to be given information about the rate of one variable with respect to time, and then you have to find the rate of the other variable with respect to time. So there's a relationship between variables, there's usually given rates, and then there's the rate that you want to find.
So will these always have like 2 answers for the different?
Yeah, well, if there's 2 variables in the equation, there's going to be 2 rates, right? Because if x is a function of t, that means x is going to be changing with respect to time. So that'd be one rate, dx dt. And if y is a function of t, there's a rate for y as well.
Okay.
So every variable has a rate with respect to t. How is that variable changing over time? Okay. And then the step 3 would be express all given rates and rates to be found as derivatives. So that's the dx dt stuff. And then you would find an equation connecting the variables, but you guys are already going to be given the equations that relate the variables. Okay. In the regular calculus class, this is way more complicated than what we're going to do here. You actually have to find these equations first using geometry from pictures. Okay, so that's the nice thing. The business and economics ones, you're already given the profit function, cost function, revenue function. Okay, and then what it says is, once you have the equation and you've identified the known rate and the rate you want to solve, you take a derivative implicitly with respect to t, and sometimes you have to use the chain rule, just like we did for implicit differentiation. Okay, so what do they give us? So here's the relationship between variables. We're pretending x and y, those variables are both functions of t. And what they say is, they say find dx dt. So how much is x changing with respect to time? Given that, so here's going to be the known rate. So y changing with respect to time is going to be 4 when x equals 3. So your units on time could be minutes, right? So this is saying like y is changing by 4 units every minute at the point when x has a value of 3. I think this will make more sense if we do an application problem in the next example. Because here it's kind of arbitrary. What does x represent? What does y represent? What are the units on time? Okay, so I maybe should have started with an application first, but at least this will give us an idea how to solve them, and then once you see the application problem, it'll make more sense. Okay. So here's what we're going to do. All we're doing is implicit differentiation again, where x, so both of these are now dependent variables. There's not even any t's up here, is there? Right? So if you need to, I'll do this for the first time, but I'm not going to do this next time. We're just going to rewrite x as x of t and y as y of t. Okay, so we have a given rate at a particular x value, and we're trying to find how much x is changing with respect to time. So what I'll do is I'll write x of t squared plus 3x of t y of t equals 4. And again, the only reason I'm doing this is just, I got to bring the t's in so you kind of see what I'm doing. Also, we're going to switch back to, we're going to use x prime and y prime for now, but just be aware that when I write x prime, I really mean dx dt, and when we write y prime, we really mean dy dt. Okay, so it's how much are those quantities changing over time? Okay. So now everything in sight's going to be taken, we're going to take a derivative with respect to t, but it's no different than what we were doing before. So take the derivative of both sides with respect to t. Is it okay if I write WRT for with respect to? Okay. All right, so how about the x of t squared? That's again just general power rule. So the 2 comes out front. The inside would stay the same. That would be to the first power. So I use the power rule on the outside, and I need to make sure to multiply by the derivative of the inside, which for us would be x prime of t. Later on when I do this, I'm not even going to write x as x of t. I would have just written 2x dx dt, because dx dt and x prime are the same. Okay, so that's the derivative of the first term. And I didn't leave myself much room again, plus, oh, I don't know why I'm doing that, that's okay though. Okay, so over here what do we have? I have 3x of t times y of t. So that's really a product. Okay, and this time I can write this down. That's the first function. That's the second function. Okay, so you're going to take the first function, 3x of t, times the derivative of the second, y prime of t, plus the second function, y of t, times And then what's the derivative of 3x of t? It'd be 3 times x prime of t. So that was product rule. I did the first function, 3x of t times the derivative of the second, that became y prime, plus the second function, y of t, times the derivative of the first, which is just 3x prime. And then the derivative of the right-hand side is just 0. Okay. Now, I'm going to convert this back into x's and dx dt's. Okay. The reason this notation is more useful is it tells you what your variable is changing with respect to, right? These quantities are changing over time. If you just write x prime, that information is lost. Okay, so if I rewrite this now in the different notation, this is 2x dx dt plus 3x dy dt. So the x prime is dx dt, the y prime of t is dy dt. And then plus, I'll do 3y dx dt equals 0. So that just becomes y, and that's 3 times dx dt. And then tomorrow when we start this, I'm just going to go straight from the beginning, straight to the x's, y's, and the dx and dy dt's. Okay.
So if we just write those as prime?
No.
Why not?
Again, you lose the information that what are these things changing with respect to.
Okay.
So it's more instructive, or it tells you more to write the Leibniz notation. Plus, they're always going to give you things in terms of dy dt. So I've seen students do this when they write y prime. They forget that y prime is dy dt, and they're like, well, what do I plug in for y prime? So it's mainly just, you got to get used to the notation because that's the notation they're going to give you.
Okay.
I don't care if you write x prime, y prime, as long as you translate back into the dx dt notation. Okay.
I think I'll just stick with what you're doing.
Yeah, it's what you're going to see in the textbook. If you go watch videos online, you're going to see this dx dt notation, so I think it's just better to get comfortable with it. Okay, so what we need to do is a couple things. Ultimately, we want to know how much x is changing with respect to time. Okay, but we also know dy dt is 4 when x is 3. The only thing I don't know is what's y. Anybody have an idea how to find y if we know x is 3? If you go back to the very beginning of the problem, we have a relationship.
Just plug in x equals 3.
Yeah, we have a relationship between x and y. Okay, so when x is 3, I can also find y. Okay, so when x equals 3, we have 3 squared plus 3 times 3y equals 4. So if you want to figure out what the other quantity is when you know the other one, you always plug it in the original equation. And then let's see, I can do 4 minus 9 and then divide by 9. Y is going to be negative 5/9, I believe. Okay. And then I'll plug all the known information in, and we'll solve for dx dt. And like I said, the good news is, this is the last time we'll have to do this. This actually is an isolated topic. We don't actually need to use this at all for the rest of the quarter. Okay, so but I have to make you do it because there's the business and economics applications. Okay. So we just have to suffer through it. Okay. And then let's see now. I'm going to plug all the known information in. I know x is 3. I know dy dt was 4. That was given. And now I know when x is 3, y is negative 5/9. So now I can substitute known values or known quantities. And you'll get, let's see, 2 times 3 is 6 dx dt. Plus, and then here I have 3 times 3 times 4. Because we know x is 3 and dy dt is equal to 4. And then it's plus 3 times negative 5/9 dx dt equals 0. Okay. So you plug in all your known quantities. And then let's see here. I think these two can be combined. So I have, this can be subtracted to the right. 3 times 3 is 9, times 4 is 36. Okay, so what I have here is I have 6 minus 15/9 dx dt equals negative 36. So out of these two expressions, I factored out the dx dt, and then the 36 I subtracted to the right. And then finally dx dt is negative 36 over the 6 minus 15/9. And let me see if I can simplify that at all. You can also just plug it in the calculator and see what you get. And then sorry I stole some of your time. I'll make it up to everybody eventually. And I just get negative 108 over 13. Okay. So the thing you might want to think of here, maybe x is your profit. And the time is the units of time might be weeks. Right? In that case, the change in profit per week, okay, that might be your change in profit per week, how much your profit is decreasing or increasing. Okay. So I did the general example today. Tomorrow we'll do some business and economics related examples. They're not as bad as this one. Right? All the functions for profit, revenue, and cost I think we're going to deal with are polynomial functions, so I don't know if it's going to be that bad. But I'll see everyone tomorrow. Have a good rest of your day.